Yeah, so as was mentioned, we're from the UW's Data Lab in the information school there, and we're going to be presenting on STEM-ming with high, predicting STEM attrition using student transcript data. As is implied by the title, we were very curious about how we could use the student transcript data that most universities have to predict when STEM students would, or students who are interested in STEM fields would leave STEM during their undergraduate years. So why is the STEM attrition question important? Well, for one, STEM jobs are increasingly ubiquitous in our economy, and they're a large driver of it. As has been pointed out in a number of studies, including this one done in 2012 by the White House, there's going to be a large deficit of applicants in these fields. The White House report said that there would be a 1 million applicant deficit by 2020. That same report also pointed out that if you could just reduce the amount of attrition from STEM fields during college by 10 percentage points from 60% to 50%, you can cut this deficit by 75%. So in this larger context, we had two questions. Our primary question was whether we could predict if students would drop out of STEM during their undergraduate careers. And then we also had a more experimental question about whether we could use the same student transcript data to model a student's intent to major in STEM or not, a STEM field or not, at every term or quarter or semester while they were in college. And this would be in order to eventually attempt to predict when a student might attrit from STEM. So, our data. So, we worked with the Office of Planning and Budgeting at the University of Washington for 2 years to get a data set of 15 million transcript records covering around 600,000 students from 1980 to 2016. This data set includes information about the classes that each student took, the grades that they got in these classes, information about major declarations, as well as demographic and pre-college entry information. We also worked with the Office of Financial Management to get a categorization of every major as a STEM major or a non-STEM major. So one important thing to note about this data set, however, is that it was limited in the fact that we didn't have financial information, so we couldn't potentially see at-risk factors from that sort of data. Also important to note is that the data set that we got from the Office of Planning and Budgeting included both graduate students and undergraduate students, transfer students and non-transfer students. But for both of the questions that we asked, we were focused solely on undergraduate non-transfer students. So the related work that we found in when we were beginning to do this research fell into two main categories. The first category were studies on STEM attrition. These tended to be studies that use survey and longitudinal data. And they mainly found that there are a number of academic variables, including grades in STEM courses, as well as the intensity of the STEM courseload during their early years, and other demographic variables that influence STEM attrition and retention. The second category of related work were more predictive, research that attempted to do predictive modeling on student data. This is, as other people have mentioned, a lot of it has been done in educational data mining. The one thing that we noticed is that the work that's been done in educational data mining has a very strong MOOC focus or focus in other online learning environments. And these learning environments tend to be much more data rich than a traditional campus setting. So the work that's been done in this setting isn't really generalizable to the types of questions that we were interested in. There were some studies that did similar research, primarily in trying to predict student dropouts from college using similar institutional data. But overall, we found that there wasn't really any other research that tried to do predictive modeling on STEM attrition on this large and heterogeneous data.
So for the two different questions, we actually use different subsets of the data. And for the first question, we only look at STEM students who first entered the University of Washington main Seattle campus as freshman entrants, and between 1998 to 2010. And STEM students refer to those students who either declared or had a pre-major designation in STEM major during their first year. And this subset included 24,381 students. Among the students, 50% of them actually graduated with a STEM degree, and then the other 50% were STEM dropouts who either graduated with a non-STEM degree or just dropped out of pre-doc. Since the data has a naturally 50-50 split, so we didn't do any extra work to balance the data set. And for the features that we used later on, it was extracted from pre-college entry data and then just the first year transcript records. And in terms of scale, there were 270,000 individual transcript records. So we did feature mapping, trying to predict a binary outcome, which is whether a first-year STEM student would graduate with a STEM major. And in total, there are around 1,400 features. Some main ones were listed here. We used pre-college entries and demographic features, such as ACT scores, and gender, zip code, ethnicity. And the other major part of the features were calculated based on course performances. In addition to GPA, we also calculated a Z-score and percentile score to help with the features. One thing to note that is we also calculate performance for STEM gatekeepers courses. These are courses such as calculus or intro to biology, physics, classes that STEM students usually have to take in their first year. So we use this for models to do our machine learning experiments. We use 80% data for training, and then the other 20% held out used for testing and reporting. And we use 10-fold cross-validation for tuning hyperparameters. And in addition, in order to know the importance of each feature alone, how important it is to STEM graduation, we also ran around 1,400 logistic regressions using each feature alone. So after running the experiments, our 4 models have pretty similar performances, while the logistic regression has performed slightly better than all of the others. What's interesting is that in our case, boosting didn't really have a significant increase in performances. But the main finding that we have here is that using just first-year transcript records, we were able to achieve 0.8 accuracy and 0.9 AUROC. And this transcript records, these registrar records, are not specific to the University of Washington. They are data that is routinely collected in all of the schools across the world. And and then we use non-neural methods. We use just plain logistic regressions to feed the data, but we were able to achieve pretty powerful results, and then we believe this reduced much power of the first year data. And this is the results from regressing STEM graduation on each feature alone. This table shows the top 5 most predictive feature. What we can see here is that course performance in math class is very crucial to a student's later on academic trajectory. The top 4 most predictive features are all derived from math courses. For example, the first 2 are course performances based on math gatekeepers classes, so intro to calculus. And then the other 2 are just general math class course performances.
So for the second question that we were interested in, as I mentioned earlier, was whether we could model a student's intention to major in STEM at every term during their undergraduate careers. In order to do this, so first of all, some context. The University of Washington does not require their students to declare a major until their second or third year. And actually, in many cases, it's hard for students to declare majors until their second or third years. And while there is a pre-major designation, as mentioned earlier, that can be applied to freshmen and sophomores, this data is fairly unreliable because it's based on data that's taken from these students' applications into college from when they were high schoolers. And a lot can change from between then and when they're actually in university. And we were also interested in more granular data about the exact term that students might be interested in STEM or decide that they're no longer interested in STEM. So in order to do that, we figured that we could look at the relationship between the courses the students taking and their intent. And we figured that there's some relation between these between that latent feature, the student's intent, and these observed features that's in our data, the courses. So we experimented with this the probabilistic graphical model of this form, where we have the series of hidden states, the X of T, which represent a student's intent to major in a STEM field. And each is dependent on the last quarter because we assume that the student's intent is dependent on whatever they were intending to major on the last quarter. And then we also have this intuition that the courses the student takes is dependent on whatever they were interested in majoring in that quarter. So that's represented in our model as each hidden state emitting a plate of course indicator variables, one indicator variable for each potential course that they could have taken that quarter. On the terminology aside, the predicted or the estimated STEM intention we labeled as STEM affinity, just to make sure that we weren't talking about something that we can actually talking about an unsupervised problem. So in order to construct this model and test it, we used a cohort of around 4,000 students, all of whom started in 2004 and graduated in 6 years by 2010. The plate of courses that we used consisted of every course taken by this cohort, so even if only a single student had taken a course, we included in that set. We assumed that the observed states were conditionally independent of each other, just to simplify the model a little bit. We initialized the prior and emission probabilities as the proportion of students who ended up graduating in STEM and the proportion of students who took a class who ended up graduating in STEM, respectively. And then we used the forward backward algorithm to just find this STEM affinity. And then we made sure to initialize the transition probabilities in a way that maximized the final core accuracy. So the amount of students who had a STEM affinity that was above 0.5 and that matched what they actually ended up graduating in. While also making sure to minimize the first quarter switches, so the number of students who switched from above 0.5 to below 0.5. So here, presented here is a case study of some results that our model produced. So this is an individual student who took the classes listed there. As you can see, the student had a very high STEM affinity when they started at the UW, and in those 2 quarters they took the Intro to Chemistry series, which is a series that isn't taken generally by students who aren't intending to major in STEM fields. But by their 3rd or 4th quarter, so by the time they were entering their 2nd year, they had their STEM affinity as produced by our model dropped, and you can sort of see that they stopped taking classes that are generally taken by STEM majors. And in fact, they ended up graduating in history. Another interesting result that was sort of produced by this model was an aggregate view of the number of students who graduated, who were intending to major in STEM or had high STEM affinity. So this particular chart shows all students who graduated in exactly 12 quarters, just to make it easier to visualize. And that was a population of around 600 students. As you can see, early on around their 1st year, a very high proportion of them had a high STEM affinity. But by the time that they were entering their sophomore and junior year, that number had fallen by 50 or 60%, which actually lines up pretty nicely with what the White House report had stated that I mentioned earlier.
Okay, I think you could wrap up.
Yeah.
I'm sorry.
This is last slide.
Awesome.
Yeah. So as you can see, some of the work is pretty preliminary and there's a lot more we want to do. For the predict model, we want to do more extensive feature engineering. And then one source of feature would actually come from our graphical work. For example, it would be really interesting to see how a student is doing compared to his peers who has a similar academic interest in a given time point. And in addition, we also want to explore more modeling techniques such as a neural network. And for the graphical model, since it's a learning problem and there's no ground truth, so we don't know a student's actual true intent at each quarter. But we still want to improve our model as we know what's the hidden state for the last state, because we know what is the actual major a student graduate with. So we hope to use that to validate and improve our model more. And more importantly, we hope to use this model to be able to predict the time point when a student will leave the STEM field. Ultimately, we believe the entirety of the work has many applications in advising at university campuses. Being able to identify students who is likely to change their academic interest will provide opportunities to develop interventions, and furthermore, the proof of concept graphical model actually allows us to do so in a timely manner. And that concludes the presentation. Thank you.